And everything in Excel in a chart is called a series. And this is the select data source and legend entries series. This is just the X and the Y that it's going to produce. So if you click Add, you get the series box, Edit Series. You can put in a name for the series. If you've got a lot of data, you can put in a name. It doesn't matter what the name is or whether it's got a name or not. So it doesn't matter. The first one that we need is the series X values. And if you click in that box somewhere, it will let you go to the data that you want for the series. And you just mark that data. And that will be the X-axis. Then the next one is Y. Mark that one. And you get the same chart as before. Same graph. They're what's called charts in Excel for some reason. And you can put on chart titles, etc. Or not. And you can edit it by clicking on the plus sign on the upper right, or go to chart design at the top. And then over to the left, it is add chart element. And this gives you the same menu as clicking on that plus sign. So put on chart titles. This is fall credits. And spring credits. And I erased my title before. And everything you do to a chart, once it is made, for titles, for the chart design, the chart titles, the background color, anything, is always the same in any chart, no matter how you got it or what it is. Once you can do one, you can do any of the others. Now we need the correlation again, and the correlation command is CORREL equals COR, and you can spell it out or double click on correlation and then mark one series and the other. And it doesn't matter what X and Y are in this. This is just two columns of numbers. If you put them in the opposite order, you would get exactly the same answer. So that's the correlation again. And you get more decimals than were ever needed. So there's the correlation. You can get a statistical significance for the correlation. And all it is R is equal to 0 or it's not. So we can test the significance of R. There is a chart in My Open Math that shows the critical values of R. It depends on sample size. We have 10. If you look at n equals 10, that's the line there at 10, And at the 0.05 level, two-tailed test, the significant value of R is 0.63. So the 0.79 is significantly different than 0. That says R is significant from 0. R depends more on the area of study than it does on anything to do with significance. If you're doing political science and you get an R value of 0.5, they think that's wonderful. 0.3 is good. If you're doing anything biological, like weight of fish from fish length, if you don't get an R of 0.9, there's a mistake. The actual significance of R depends more on what you are doing than it does on the table. So anything to do with people, opinions, and so forth. If you get an R of 0.3, they have a party. If we're doing fish length and fish weight and we get an R of 0.3, there's a mistake. There's a problem. R shouldn't be any less than 0.9 for anything biological. It's got much more to do with the subject matter than it does anything else. Also, R does not mean cause. This is we had one with bed sheets and consumption of cheese, and the R value was high. There are all kinds of examples of spurious correlations. Number of doctors in a country and chocolate consumption has a very high significance. Global warming and average life expectancy. Number of PhD applications in honey production. R does not mean cause. Back to the graph. Look at the graph. This is used to predict the number of spring classes that would be needed based on the number of people in the fall. How many people took math in the fall? And they'll need a class in the spring. But look at the chart, and for a community college, there's two varieties of students, basically. One is they're taking classes full-time and they're going to transfer somewhere. The other one is people who are taking classes part-time and eventually they might transfer somewhere. So they aren't taking a full load of credits. If you look at the graph here, you can see there's two groups, and you can use the R value to separate the groups or to look if the groups are separate. Here, this is the upper data. People who are taking more credits, which puts them on this upper track here. And if we get the R value for that equals COR, and it doesn't matter which one's first. They're completely independent and they may have nothing to do with each other. The R value is 0.89. It's much higher than the one we got before of 0.79. And this is the lower group. And if we get the correlation for this, mark one, comma, mark the other. We get nearly 1 for the correlation, a nearly perfect correlation. So I can use the R not only to describe the relation, but also to look for a separation. So that R is just more than a correlation. You can use it for a test of, are these things different? That's correlation. Now we need linear regression. This is simple linear regression. We're going to predict. If we have fish length, we want to predict fish weight. When they are checking deer at a check station, they check the heart girth of the deer. That's a measurement around right behind the front legs. And that's well related to weight. This is also used for cattle. You can estimate the weight of a cow by measuring the heart girth. And they can estimate your weight pretty well by measuring just under your arms around. But they want to measure one variable, usually called X, to predict the Y variable. So this is prediction. This is pure, I want to know something. X is usually easy to get. And it's going to be the independent variable. Y is the dependent variable because it depends on X. Also, X can be the predictor and Y is the predicted. Right? And they're just generic names. It's simple regression because there's one X and one Y. Fish length and fish weight. Or heart girth and cow weight. And it will only handle straight lines. Right? We got no curves in here. We can adapt it, but simple linear regression basically is one X, one Y, and a linear relation. All right, you remember what they taught you in algebra class for a straight line. Y equals mx plus b. What is m? It's the slope. How do you define slope? Rise over run. This is purely rise over run. We want a straight line that will predict y from x. So we've got points in here. This is x, this is y, and we want to put a straight line through it. So if we pick a value for x, we go up to the line and go over, and that is the predicted value of y. This is purely a straight line, just like you've always done a straight line. Right? If I have 2 points, I've got x equals 2, y equals 5, and x equals 7, y equals 15. Why not? What's the slope? Rise over run. How much does y change from 5 to 15? 10. So the rise is 10. What's the run? 5. So the slope is 2. Once I've got the slope, how do I find the b? It's the intercept. It's the y-intercept. And I get it by, once I have the slope, I go backwards. Y minus mx. I put in the slope, I pick an x and a y, and I get the intercept. This is exactly what we're going to do for simple linear regression. The difference is I don't have 2 points. I've got a whole bunch of points. Here's the fall and spring credits. I want to put a line through there. A straight line that will allow me to predict fall credits or use fall credits to predict spring credits. But I've got more than one or more than 2 points. I can't use the regular rise over run. I still have a version of rise over run, but it's calculated differently. It's got a fancy formula, but in Excel, what do you suppose the command for slope is? And do equals start to type slope. This is going to give us the slope of the line between the x and the y. This is a version of rise over run that uses all of the points. But in simple linear regression, you use the slope command to get the version that will predict the rise over run. When you've got the slope command, look at what it wants. The order here is important. When I did correlation, it didn't matter which one was first, which one was second. In this, I have to do the y values first. So for this, we're predicting spring credits from fall credits. Spring is y, fall is x. So we need to do the known y's first, and you just mark them. Comma, and then do the known x's. Close it, and the slope, and again, you can't use all those decimals, they mean nothing. The slope is 0.76. What does the slope of 0.76 mean? What are the measurement units of slope? It's rise over run. And it's always been this, even when they did y equals mx plus b. This means for every one change in fall credits, the spring credits change by 0.76. And this is just like here, where we had a slope of 2. If you change x by 1, y changes by 2. So the slope is the change in y for a unit change in x. So if I add one more fall credit, spring credits goes up by 0.76. If I knock it down by 1 credit in the fall, spring credits reduce by 0.76 credits. Now I've got the slope 0.76x plus the intercept. When you've got the 2 points, how do you find the intercept? Here's my points, 2 and 5, 7 and 15. Slope is 2. The intercept is b equals, and I just pick one. I can use either point, 5 minus 2 times 2. 5 minus 4 is equal to 1. So the line through those 2 points is y equals 2x plus 1. When I've got a bunch of points, I can't do that. I have to use the average x and the average y. So to calculate the intercept, it's b is equal to the average y minus the slope times the average x. That's the way it's calculated. What it means is that the simple linear regression line always goes through the average x and average y. It's forced there. And if I do this, I find the intercept exactly the way you did in algebra class, except average x and average y. The line will always go through the average x and average y. But in addition, If I'm using XL, how do you think I find the intercept? Type intercept. Pick a spot, equals INTER, intercept, and again, Y is first. It always tells you what it wants. Known Y's first. I'm predicting spring credits from fall credits. So I got to do spring credits first and then fall credits. And here the intercept is about 2.1, 2.15, 2.16. So the regression line, the best fit line, the line that can't be improved on, goes through the intercept of 0.2 or 2.16 and has a slope of 0.76. Go back here. We want the average x and the average y. And you can get this with the automatic command or just equals average. Average there. Average is 10.6, and if I just copy it over to the y's, well, didn't copy it, moved it. The average x is 10.6, the average y is 10.2. I'm going to put the line on that graph. And the way I need to do it is I got 2 points now. I've got average x, average y, and I've got the intercept. So I want my line to go through x and y, 10.6 and 10.2. This is going to be my x column, and this is the y column. For the intercept, what is the value of y for the intercept? It's the intercept. What's the value of x? It's the y-intercept. What's the value of x? 0. So this is going to go through 0 and 2.155. I'm going to add this series to the graph. I'm going to plot this line. Get rid of that one. Right-click in the graph and go to Select Data. We're going to add another series. Select Data. Here's the one we've got. If you gave it a name, it would show the name. We want to add another series. And I'm going to call this one line. It doesn't need a name, but I've got one. Then mark the x values. There's only 2 of them. Then mark the y values. Click OK, OK, and there is my line. You see a line? I got 2 points, no line. Pick one of the spots. This is the average x, average y, and this is 0 and the intercept. I want the line to go through there. I need to alter this series. And again, if you can do this on one graph, you can do it on any Excel graph. It's always the same. Right-click on that spot. You get the menu for this, and one of the entries is Format Data Series. Format Data Series, and you get a paint bucket, a pentagon, and a bar chart. And each one of these has got something different on it. This one, the bar chart, you can put another axis on there. It doesn't do much. This one is always the same. It does special effects. This is the one that makes a difference. We can put a line in and markers. If we're in line, we can do a solid line. And you can change the color of the line. You can change the weight of the line. You can change the style of the line. All kinds of stuff. But now I have a line. The markers, the marker options, is the one I've got right now is automatic. I can change the color of the marker. I can remove the markers entirely. Or I can change it to a different kind of marker. And I can change the color. That's a really pukey orange. And I can change the weight of the markers, on and on and on. There's the line. This is called the line of best fit. And there's a definition for best fit. My line doesn't go all the way across. I want to draw the line with an X of 20. That way I'll get my line that goes all the way across the graph. So I want X equal to 20. How do I get the Y value? What's the slope and the intercept? 0.76 is the slope. This is y equals mx plus b. I've got a slope, an intercept, and a value for x. I put in x equals 20. I multiply that by 0.76 and add the intercept. So this y value is going to be equal to the slope times my x value plus the intercept. And the answer is false because I equaled instead of plussed. There we go. That should do it. So the predicted value of y at x equals 20 is 17.3. I want to add that to the series I have of the intercept and the average. Right-click in the graph, select data again. I'm going to go to line and then edit that series. I leave the name, that's good. Click in the X, I just want to extend it to get the 20. Then in the Y, extend it to get the 17. And there is the simple linear regression line to predict the spring credits from the fall credits. All right, suppose someone took 10 credits in the fall. What is the predicted value of the credits in the spring? Go to 10 on the x-axis, go up to the line till you hit the line, and go over. And that's the y value. This is just the official way. Equals this 10 times the slope plus the intercept. And the predicted value is 9.74. I'm going to add this point to my graph. And it's just one point. Going to right-click in the graph, select data. And this is always the same thing. Now I'm going to add a series, and it's going to be for x equals 10. Give it a name. Select the x. Select the y. And there is the point, right there. I'll change the marker. Solid fill, I'm going to make it red. The border, solid line, I'm going to make it red. And I'm going to bump up the size. So I've added the predicted value of y for x equals 10. What was the actual value for someone who took 10 credits in the fall in the original data? Look for a 10 in the x's. It's 11. My prediction was 9.74. The difference between the 11 in the original data and the 9.74 is called a residual. It's a mistake. I put in 10, I got 9.74, and the actual value was 11. I missed by 1 1/4. The definition of the line of best fit is the line that has the minimum value of the accumulated mistakes. Like for this one, where the point is 6 in the fall and 10 in the spring, my predicted value would be on this line down here. The distance between the line and that point is the residual, is the mistake. The line of best fit, the simple linear regression line, and this goes back to the slope, is the line that minimizes the residuals in some way, minimizes the mistakes. No other line I put through there will do as well. To determine how good the line is, I have to look at the distance between each point and the line that predicts those values. I made a mistake. I missed. It was 11. I got 9.74. If I put any other line through there, I would make a bigger mistake than the 1 1/4.